So let X be the number of widgets a company makes. And so that, yeah, that's just gonna be a count. The unit on X is just the, widgets. And let's the function C of X be the cost of manufacturing X widgets. Okay. So now a manufacturer might want to ask, how should we decide how many widgets to make? If we're making like 100, how do we decide if we should make more or if we should make less? What makes sense from a business perspective? So what economists do is they look at what's called the marginal cost. So they say, well, if you're making X widgets, let's look at the cost of making one more widget. Okay. How does that change the overall cost? Well, the change in cost, delta C, is that, right? The difference in costs. And so what economists do is they say, let's look at the change in costs with respect to the change in the number of widgets we make, just by adding one. So delta X is going to be 1. This is called the marginal cost. And economists say, well, this marginal cost, delta X over delta C over delta X, that's approximately equal to the derivative of C. So from a computational perspective, we're going to look at the marginal cost as being the derivative here, and it's going to tell us the cost of making an additional widget. It's an approximation, but that's okay. This is how they do it. Okay, they use the derivative. Okay, so I'm going to underline that. Marginal cost. Likewise, or maybe similarly, if R of n is the revenue generated, our variable is X. R of X is the revenue generated by making X widgets, and that'd be in dollars. And if P of X is the profit generated by making X widgets, and that's also measured in dollars. Okay. We can talk over, the economists can talk about marginal revenue and marginal profit. And in the language of calculus, it's just the derivative. Okay. So this is how economists apply calculus to the work that they do. I guess it's also worth noting, and I'll go to the next page so I'm not writing too low on a page. Profit is defined to be revenue minus cost. So the marginal profit is the marginal revenue minus the marginal cost. Okay, by our rules of differentiation. Okay, so let's just do how might you run into this in real life or later in the course? Consider this example. An apartment complex has 250 units to rent. If the manager of the complex rents X apartments the property generates a profit given by this function. P of X equals minus 8x squared plus 3200x minus $80,000. Okay, so there's a profit function. So a natural question to ask if you own these apartments is, what's the break-even points for the apartment complex? When does the complex break even? That is, when is its profit zero, right? When is the same amount of money coming in as is going out? So this isn't the calculus question. This is just a pre-calculus question. So we want to solve 0 equals minus 8x squared plus 3200x minus 80,000. And you just use the quadratic formula. So the solutions to this are x equals negative 3200 plus or minus 3200 squared minus 4 times minus 8 times minus 80,000. All of that under the square root. Then everything divided by 2 times the negative 8. Then if you do the work, you get two answers, 26.79494 and 373.2051. Those are the two answers from the quadratic formula. So what's the answer to the original question? When does the complex break even? Well, first thing you should recognize is you can't have a fractional apartment, right? So should we replace this with the number 26 or should we replace it with the number 27? Well, if you're breaking even at 26, it's probably the case that if you rent the number of apartments that's fewer than 26, you're gonna likely be negative, right? You're not gonna break even there. But if you replace this with 27, right, you'll be making a little bit of money. So let's put that one in there. So x equals 27, or then how about that 373.2? Well, I don't know really how to argue that one, but if you wait a second, if we use the same logic and we round up, right? We'll just use the same logic. You could say round to the closest and round down. It's probably good to explain whenever you round what you do, but let's just put 374 for now. And you'll see immediately that it's irrelevant. And it's irrelevant because you only have 250 units. So you can't even consider, I mean, the number 374 doesn't make sense in the context of our problem. So this is the only number that makes sense. So we can write, we say the complex breaks even when it rents 27 units. So the next question we want to ask is, well, what's the marginal profit? Okay, for renting a unit. So the marginal profit is the derivative of the profit. And so that's the derivative of minus 8x squared plus 3200x minus 80,000. So using our rules for derivatives, that's minus 8 times 2x plus 3200 times 1 minus 0. So we get minus 16x plus 3200. So that's the marginal profit. So how do we use that? Well, if we ask when is the marginal profit 0, because if there's no additional profit to renting an additional unit, you just want to stop, right? You're getting all the profit you can up to that point. So if you look at when is the marginal profit 0, then you use the formula we calculated and solve. And it looks like we get x equals 200. So renting 200 apartments is kind of where we don't get any additional profit from renting another unit. And so economists would say that's where you're maximizing your profit. So the point where we have no additional marginal profit is when we rent 200 units. So let me just give you a little insight into what's happening here. So here's a graph of the profit function. So here's the number of units. Here's the profit axis. And the graph of this function, you can plot it yourself, looks like this. So we only go up to 250. We go from 0 to 250. We determined that this intercept is right around 27. Is that what we said, or 26? 27. So right here is 200. Right here is where the tangent line is horizontal. And you can see up until 200, our profits were increasing. And then after 200, our profits start to decrease. So looking for the place where the marginal profit is 0 is a way to figure out where that dynamic happens or potentially happens. And that's why economists say finding where your marginal profit is 0 is a way you can maximize your profit.
I had a quick question, Professor.
Yes.
And I know we'll probably just be given like the polynomial, but I was curious as to, for negative 8x squared plus 3200x minus 8,000, was that 80,000? Um, what exactly do those numbers mean? Like, according to the problem? I know, yeah, I know. I know that's more like a business type of question. I'm just kind of curious since we're talking about it.
Okay. No, it's a fair question.
If it's not too long of an answer, it won't take too
Okay,
much.
so I've copied this over so I can recopy it. So let's imagine that we have this profit function. Okay. So did I get your last initial right, Alexia? Yeah. What could these coefficients mean? Okay. So let's just play the game and see if we can make anything out of it. So I'll write it this way. Profit is revenue minus cost. So if we wrote our function up here, a natural way to rewrite that profit function, just for the sake of having a conversation, might look like this. Okay. So you can imagine a reasonable person might say, well, maybe this is the rent, $3,200. So for every unit you have, you're going to get $3,200 in rent. Okay, so that would be your revenue. And then over here, what's happening is you've got two things. You've got a term here that depends upon X, the number of units you rented, and you've got a term here that represents it's a fixed number. It's independent of X. It doesn't change as X changes. So an economist might call this a fixed cost, and maybe it's the manager's salary. And this here is a variable cost. And so imagine that this 8 here might represent a utility cost. And for some reason, your utilities increase at a rate that's squared by the number of units you had. Maybe there's an increase in efficiency the more people you have living in your apartments. But this is one way you might see it. And if you were doing a problem and I were expecting you to build a function, I would give you some language that would suggest that you'd have a square function here. Okay. But if I were asked, as Alexia asked me, to try to maybe interpret this function in terms of real life things, this is one way I might try to do it. Is
Okay.
this good, is that good?
Yeah. Thank you. I appreciate you explaining that.
Yeah.
All right. Thank you.
Mm-hmm. Okay, so what time is it? We're at 8:51. It is time for a break. So let's take a break for 5 minutes, and then I'll say a couple more things about rates of change, and then we will talk about the chain rule. We'll finish the day with the chain rule. All right, so I'm going to set my watch, my timer, for 5 minutes. And then I'm gonna get some more coffee. So I'll see you back here in 5. I'll pause the recording. Recording, right?
Yes.
Yeah, right. Thanks. So velocity also tells us direction. When our velocity is positive, our direction is moving to the right. When our velocity is negative, we move to the left. And when our velocity is 0, we're stationary. We're not moving at all. So these are important interpretations of velocity. And then I'll just add one more thing. If velocity is differentiable, we say the derivative of velocity is the object's acceleration. The rate of change of velocity is acceleration. And the unit on acceleration is the distance unit divided by the time unit squared. Okay, so for example, a unit of acceleration might be meters per second squared. That's a unit that physicists use to describe acceleration. like the acceleration due to gravity, for example, and that's 9.8 meters per second squared. So let's put this stuff to use with an example. Suppose I've got an object. Its position on a straight track. Is given by this third degree polynomial s of t is 1/3 t cubed minus 11 halves t squared plus 28t plus 4. Where t is measured in seconds. Okay. And s is in meters. So question, what is the object's velocity? At time t. So we're given a position function and we're being asked what's the velocity function. So velocity is the derivative of position. So I want to take this position function and differentiate it. V of t is s prime of t. So we're going to take the derivative of s. So by the sum rule, I can differentiate term by term. And then each of these terms are a monomial, so I can use the power rule. And so we get, for the first term, the derivative is 1/3 3t squared. The second term, it's 11 halves times 2t. The third term, it's 28 plus 1. And the fourth term is a constant, so its derivative is 0. So simplifying, there's my velocity function. That gives me the velocity of my object at any given time. Another question that we could ask would be this: when is the object stationary? And while you could say that this function here suggests that my function, my object is always changing position, so it's never stationary, but that's an oversimplification. It turns out when you go from moving to the right to moving left, right at that very change in direction, you have to be stationary for a second, because moving right, your velocity is positive. Moving left, your velocity is negative. So somewhere between the positive and the negative, because velocity is continuous, your velocity must have been 0. So that's why we say asking the question, when is the object stationary, is the same thing as asking, when is the velocity equal to 0? So let's take the velocity function that we computed in the last problem, that quadratic. Set that equal to 0 and then solve. You could use the quadratic equation here to solve it. That's perfectly legitimate. But you could also see that 28 factors into 7 times 4, and 11 is 7 plus 4. And so that suggests that the polynomial can be factored in that way. And you have to just be careful that the signs you choose here give you the proper signs there. So that's the factorization of that. And so we can see that the object is stationary at t equals 4 and 7. And maybe I should put the word seconds. So let me ask one more question about this. So when is the object moving to the left? So moving to the left, we said that's when the derivative is negative. And if it's not clear to you why that is, go back and think about how the derivative is related to this average rate of change. And see if you can make the connection. That explains why we say this. So we want to find out where the derivative is negative. Well, we've calculated that the derivative can be written in this way. So now I need to solve this inequality. So there's a technique that I want you to be able to do. It's called a chart of signs. And what you do when you want to solve an inequality, the first thing you always do is get a 0 on one side. Okay. And then we're going to make a number line. And on that number line, I'm going to put the places that the left-hand side vanishes. So where's my function actually equal to 0? And we calculated that to be 4 and 7. And now I'm going to make two rows here, one row for each of the factors, t minus 7 and t minus 4. These are the things that contribute to my derivative changing sign, maybe from positive to negative. That's what I'm putting here. And notice when I take the product of these two things, I get v of t. So what I'm going to do is that I'm going to look at each of these separately, and then I'm going to look at what they do together. So specifically, I want to look at each of these terms and decide on this subinterval here. So these vertical lines break the real line into subintervals. So I want to ask, is my factor positive or negative here? Is it positive or negative here? And is it positive or negative here? One way you can decide that is because I chose these to be linear functions, their sign will only change once in the whole real line. So, and 4 and 7 are the only places where my velocity function can change sign, because that's where my velocity function is 0. So if these functions change sign, they have to change at 4 or 7. So what I can then do is I can just pick a number in each of these intervals, plug them into these factors, and see if each factor is positive or if it's negative. So for example, on the first interval here, I might choose the number 0 because the number 0 is down here. So I plug 0 into this factor, I get 0 minus 7, which is negative 7. So that tells me that factor is negative on that interval. It's negative on that whole interval. And for the same reason, I get the other factor is negative on that whole interval. Next, I'm going to look at this interval. I'm going to pick a number in here, say 5, the number 5. And I'm going to plug 5 into both of these. So for the first factor, I get 5 minus 7, and that's a negative 2. So that tells me that the factor t minus 7 must be negative on the whole interval, because it can only change sign at 4 or 7. The other factor, plug in 5, I get 5 minus 4. That's the number 1. So that factor is positive on that whole interval. So now I have the signs of the two factors on two subintervals. Last subinterval, I'm going to pick the number 10. So plug that into the first factor, 10 minus 7. That gives me a 3. That tells me that that factor is positive on that whole subinterval. Plug 10 into the other factor, 10 minus 4, that's 6. That's positive. So that factor is positive on that whole subinterval. And now you can look, this is called a chart of signs because I'm keeping track of when each of these factors are positive and negative. They can only change sign at 4 or 7. And sure enough, look at the factor t minus 7. As I go up the real line, it only changes sign once. And I knew that was going to happen. Look at the other factor, t minus 4. Go up the real line. It only changes sign once right there. Okay, so now what do I do with this? Well, my velocity function is the product of those two factors. And so the sign of the velocity comes from the sign of these two things. In fact, the sign of the velocity is the sign of the product of these two things. A negative times a negative is a positive. A negative times a positive is a negative. And a positive times a positive is a positive. So this gives me the sign of the velocity function on the real line. I'm looking for where the velocity is negative. So this is the interval of interest. This is what I'm looking for. So I conclude this shows v of t is less than 0 when 4 is less than t is less than 7. This means the object is moving left on the time interval 4 to 7. Okay. So this idea of left and right is something that we can interpret about a position function from the derivative. And that's something that's important for you to know. And this if you've never done a chart of signs like this before, this is something that's really helpful. It really helps you keep track of ideas when things get complicated and messy. So I want you to be able to use a chart of signs like this. If you've never seen it before, I made a couple screencasts on what charts of signs are and how to make them and use them. And I think I put a link to those screencasts on our Canvas page. Let's do let me say a couple more things. I won't do another example. Another special type of position function is a height function. Okay, and you might see this when you throw something into the air.
Professor, I have a really quick question. Sorry.
Yeah.
I was just wondering, because we got the 7 and the 4 from like when we were finding out when it was stationary.
Yep.
What happens if like you can't factor after you like get that formula, like the t squared plus 11t plus 28, like that one happened to factor, but like how would you get those numbers if you couldn't factor? Or can you always factor? I really remember factoring.
No, that's a good question. So I'm going to swipe back a page. And so what I hear you asking, Summer, is you get to this point, you get a formula for the velocity function. And, you know, you're asked, when is the object stationary? What if you can't factor that? Well, that means that there's no places where the object is stationary. So that might be the answer, right? It never stops. Yeah, you could use the quadratic formula, but sometimes the quadratic formula will tell you that you only have complex solutions, right? You don't have real solutions. And so if there's no solution to, you know, v of t equals 0, or right here, v of t equals 0, then that means the object never stops. And that's certainly a possibility, right? So if I had a position function that looked like this, I mean, that's never stopping. All the tangent lines to this thing are positive. So it could certainly happen. I would never intentionally do that to you on a problem, right? I would never ask you, you know, when is the object stationary, when the answer was it's never stationary. I'd at least try to give you a hint that might be a possibility. But it's a good question.
Okay. Because then you
Now,
couldn't, it would be hard to find the numbers for when it was moving to the left, right? If you couldn't
exactly.
find when it was stationary.
Right.
Okay. Okay,
That's right.
thank you.
Unless it's always moving to the left, right? If it's never stationary, then you can just plug in any point to your derivative. If it's never stationary, then it's always going to be negative or it's always going to be positive. And so you could
Okay.
still answer this question. It would just be never or always.
Okay, gotcha.
So another possibility is that you get a function here and your mind just blanks. You don't know how the hell to find a zero. Okay, you forgot the quadratic formula or whatever, right? What can you do? Well, you can always plot a graph, right, and look for where the graph crosses the x-axis, and then find the approximate solutions. That's always a tool you have at your disposal. Sometimes it's not the ideal one, but if you can't do the ideal thing, well, at least do something. Okay. So that's another thing you could do. And sometimes that's all you can do. Sometimes that's all you can do. So be prepared to do it. Okay, is that good, Summer?
Yes, thank you.
Okay, good. So back to this example of a height function. So you throw something into the air. So what's the number line in this case? Well, the number line is like the height, like the distance off the ground. So even though I like to draw a number line horizontally, in this type of answer, the number line is really measuring the height upward, right? Distance above the ground. And in many ways, negative numbers don't make sense unless unless you're on unless you're on a hill or something, right? A number line would represent, maybe the object going lower than where you threw it from. So the point I'm trying to make here is that a special case of position functions or height functions when you're throwing things, and the number line, you can think of that as measuring the height of the object at any given time. And so notice when your object is going up, if you're throwing something up and it changes to start going down, that's a place where the horizontal tangent line or the tangent line is horizontal. So that's a stationary point. That's where the velocity is zero. So when you're going up, you're moving right on the number line. When you're going down, you're moving left on the number line. And so it's where that point or where your object changes direction, where the velocity is zero. Sometimes these are called a turning point for that reason. Places where v prime is zero or can be called turning points. All right, so I'm not going to do any more examples of this because I think we've talked about it a bunch. But if you work some problems and when we come to class on Wednesday, you want me to do some more examples with position functions and velocity functions and acceleration functions, I'm happy to do it. You just ask. But I want to move on to the chain rule, because this is a really important rule for differentiation. And so I'm going to state, well, before I state the chain rule, we've already seen some rules for differentiation that start with, say, having a couple functions. And the rules we saw told us how to differentiate new functions made out of them, like a constant times a function, or the sum or difference of the two functions, or the product of the two functions, or the quotient of the two functions. So we have rules for differentiating these new functions based on the derivatives of these old functions. But the one rule we don't have or the one way to combine functions we haven't talked about yet is composition. So what if one function is inside the other? So we got kind of two rules that are stacked. Oops, I did this in the wrong order. So or the first function g takes x to g of x, and then the second function f takes g of x to f of g of x. And it's this sort of chain of rules that the chain rule talks about. Okay. The first link in the chain is g, and then you apply to that the function f. So if f and g are differentiable, what's the derivative of a composition? That's what the chain rule talks about. And let me give you an example of a couple compositions. Consider the function f of x equals the square root of x squared plus 10. This is a composition of two functions, or we can think of it as a composition of two functions. So if you look at the function, consider the function a of x equals x squared plus 10, and b of y equals the square root of y. Then if you consider the function b composed with a of x, that's b of a of x. A of x is x squared plus 10, and b is the square root function. So there you can see this function f of x is the composition of these two functions a and b. So if I knew what the derivative of a is, and if I knew what the derivative of b is, the chain rule is going to tell us how to take the derivative or write down the derivative formula for the composition b composed with a. Another example where this occurs, well, let me stop for a second. What I just did here is I took a function that was pretty complicated, more complicated than can really be dealt with the rules we already have. So I take this complicated function, and I recognize that I could combine these two simpler functions, right? This is a power function. This is a polynomial. I could combine these simpler functions using function composition to get this function. And this is a great trope in the philosophy of science and the history of science. And it's called reductionism. Complex problems can be reduced to simpler problems. So the solution to a complex problem can be built out of the solutions to simpler problems. That's what this demonstrates. So one skill that you're going to have to practice is seeing a complex function and being able to rewrite it as the composition of two simpler functions. So that's one prerequisite to what we're doing today. So let's look at another function. Let's consider the function g of x, and let's say it's 2x plus 10 to the 50th power. Now, this is a complex function because this is so big. You could use the binomial theorem and expand this out and take the derivative, but that would be a lot of work, and mathematicians always want to find an easier way. If there's an easier way to do something, they're willing to do it hard the first time, but then they will kind of look around for other ways to simplify or streamline. And it turns out here that if we take a to be 2x plus 10 and b to be the monomial of taking the 50th power, then the function g here can be decomposed into these two functions. B composed with a, which is b of a of x, and a of x is 2x plus 10. And then b of 2x plus 10 is 2x plus 10 to the 50th power. These are two simpler functions that I can certainly take the derivative of. They combine via composition into this complicated function we began with. So the question is, how do the derivatives of these two functions help us compute the derivative of this function? And that's what the chain function or the chain rule tells us. Any questions about this?
Yeah.
Okay, go.
Honestly, like, okay, I understand the first part when you get to y to the 50th, but after that, I really don't understand what you're doing, or like how, I just don't know how you know to do that. And I know it's from those rules you just gave us, but I don't know.
Oh,
I'm so
oh,
confused.
you're saying from these rules?
Yeah.
No, not at all.
Oh,
What
okay.
what 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 I'm doing here has nothing to do with this stuff. The
Oh,
only right, so the only thing I want you to notice is that function composition is not in this list of ways we combine the functions.
oh, okay. So the
This is right. This is just algebra. Function composition is totally different. Okay. Algebra is stuff that comes from numbers. You can't combine numbers in this way, right? So that's what I'm trying to draw that distinction out for you.
okay.
Um,
But
okay, but let me go back and just be very clear about what I'm trying to tell you here. I'm not giving anybody a differentiation formula yet. I'm not telling anybody what the chain rule is yet. What I'm trying to draw your attention to is that, oops, I want to do this in red, that these are two examples of functions that aren't unusual. There's nothing bizarre about these functions. But they're functions that we can't use these rules to differentiate easily. We could maybe do them from first principles, but we don't. These rules can't immediately be applied, but this chain rule that I'm going to tell you about can be applied. But in order to use the chain rule, I just wanted to remind you about function composition, what it is and how it works. And that this complicated function here, or relatively complicated function here, can be written as two simple functions that when combined by composition, give us this slightly more complicated function. Is that okay, Alexia?
yeah. Um, well, what exactly are you doing? You said B of A. Okay, so you're putting A of X into B.
Correct. I'm doing what I did here, except with A's and B's instead of F's and G's. So my first function here, so X goes to A of X. That's this first step. And then the function B takes what it got from the first function and takes it to the second function.
Okay.
So let me state the chain rule, and we'll do some examples, and then we'll
Okay.
circle back around it to see if it's become any clearer for you, because maybe what you're waiting for that punchline. I haven't given you the punchline that is the chain rule.
Okay, thank you.
So the chain rule, okay, this is a theorem. It says this: suppose f of x is differentiable at g of x, or no, sorry, at f at x naught. And suppose g of y is differentiable at y naught, which is the output of f at x naught. Then the composition function g composed with f is differentiable at x naught and the derivative at x naught is the derivative of y, or derivative of g at y naught times the derivative of f at x naught. Right? That's the chain rule. the derivative turns composition into multiplication. Composition of functions here becomes multiplication of derivatives here. So this is one common way to look at the chain rule. Let me write down another interpretation. Hold on. G composed with f prime at x naught is g prime of f of x naught times f prime of x naught. So this is a way some people like to write down the chain rule because it reminds them that f is at play. Okay. This first way I wrote it down kind of hides the role that f plays in the first term, but here it makes it clear. And then if you look at the left side here, as this is the derivative of g of well, let's not write it that way. Let's come over here. G composed with f at x, right? That's g of f of x. So if you call f of x the inside function because it's inside g, right? You can see it's inside g. And by contrast, you call g the outside function. The chain rule says that the derivative of a composition is the derivative of the outside at the inside times the derivative of the inside. That's what the chain rule says. And we could write the chain rule using Leibniz notation too, but I'm not going to do that right now. This is enough for us to digest as it is. So you can see that if I've got a function and I can write it as the composition of two simpler functions, then the derivative of the complex function is the product of the derivatives of the simpler functions. So that's where the value of this chain rule is. So let's go back to those two examples that I started before. So f of x is the square root of x squared plus 10. So let's write this as a composition. So my inside function is x squared plus 10, and my outside function is the square root function. Okay. So we just notice that b composed with a of x, which is defined to be b of a of x, and a of x is x squared plus 10, and b is the square root function. So I'm taking the square root of whatever's inside b. Okay. So this verifies that if you compose these two simpler functions, we get back our original function f of x. So by the chain rule, f prime of x is b prime of a of x times a prime of x. So now I just need to calculate the derivatives of a and b. So what's the derivative of a? Well, a is just this polynomial, so those are easy to differentiate. It's 2x plus 0. I'll write that as 2x. That's cool. And what's the derivative of y? Well, y is a monomial. The square root of y is y to the 1/2. So I can use the power rule, and I get b prime of y is 1/2 times y to the negative 1/2 power. All right, so I'm using these. We see the derivative of f, which we said is b prime of a of x times a prime of x. Now we'll start filling things in. So b prime is 1/2 of the input to the negative 1/2 power. And a prime of x is 2x. So I get 1/2 of x squared plus 10 to the negative 1/2 times 2x. These twos cancel. That's kind of cool. And I can turn my negative exponent into a positive exponent by rewriting it that way. And then I'm going to end using radical notation because that's the way the problem is stated with radical notation. So I get that. That's the derivative of this complicated function. So soon you'll practice this enough where you're going to see this function and you're going to go, okay, that's x squared plus 10 all to the 1/2. And then you're going to see that this is a composition. You're going to say, okay, here's the inside function and my outside function is to the 1/2 power. And the big hint to that decomposition are those parentheses there. But then you're going to say, okay, by the chain rule, the derivative is this. Well, you're going to differentiate the outside function. So 1/2 times x squared plus 10 to the minus 1/2, right? And you're going to leave the inside stuff alone, right? Because in the chain rule, you leave that inside stuff alone. So here you're using the power rule, you're getting your new coefficient and your new exponent. And then the chain rule says, okay, now I've got to put the derivative of my inside function. And that's 2x. So pretty soon you're going to be able to look at these problems. After you've practiced them enough like this, you're going to be looking at them like this. And this is the same as that. All right, I've got 8 more minutes. Let's do another example here. Let's do this other one. Black. So here's 2x plus 10 to the 50th power. Let's decompose this into the composition of two functions. So I'm going to see my inside function here, and the hint is these parentheses, of course. And then my outside function is the power function of raising to the 50th power. And let's just check to make sure this works. So b composed with a of x is b of a of x. A of x is 2x plus 10. And b raises its input to the 50th power. So the composition looks like that. And sure enough, that's my g of x. So next I'm going to differentiate using the chain rule. So g prime by the chain rule is b prime at a times a prime. So if I look back up where I defined b and a, you can see that the derivative of a is just 2. And you can see that the derivative of b by the power rule is 50 times y to the 49. So down here, I've got b prime at a, and a is 2x plus 10. And then I've got a prime, we said that's 2. And now b prime, we said b prime takes the input, multiplies it by 50 after raising the input to the 49th power. So there we go. There's the derivative. And it won't be long before you're differentiating something like this, or something like this in the following way. You see 2x plus 10 to the 50th power. You immediately recognize that here's the inside. And so the chain rule says the derivative of a quotient of a composition is a derivative of the outside. And in this case, that's raising to the 50th power. So oops, let's do blue. So do the power rule, leaving the inside alone. And then you got to do the chain rule, multiply it all by the derivative of the inside, right? So there's the inside, and the derivative is 2. All right? Pretty soon, this is how you'll be doing the chain rule with sufficient practice. So let me show you one more thing in the few minutes we have remaining. So suppose g of x is a differentiable function. Since, let's see how to write this. Since z, which is y to the nth power, the power function is differentiable. The function z equals g of x to the n is differentiable. Let's calculate z prime for n equals 2 and 3. Okay, so let's differentiate g of x squared. Here's n equals 2. Well, we don't need to do anything fancy here because we can just use the product rule. So the derivative of the product is the derivative of the first times the second, plus the first times the derivative of the second. Multiplication is commutative, so these two are the same. And so I'm left with 2 times g of x times g prime of x. Okay, done. Now notice, I'm differentiating this. If g is the inside function and squaring is the outside function, I could use the chain rule to say, let's differentiate the outside function. Take my exponent, put it down to the front, reduce the exponent by 1, and then multiply by the derivative. And by God, that's exactly what this is. So we've basically verified the chain rule for this special type of composition. Now let's do that for n equals 3. So I'm going to write this as g of x times g of x squared. And I'm going to use the product rule again. So product rule says the derivative of the product is the derivative of the first times the second plus the first times the derivative of the second. We just calculated the derivative of g of x squared. It's this. So I can recopy this in for this. And what do I get? I'm going to start up here. I don't have a lot of room. I get g prime of x times g of x squared plus g of x times 2g of x, g prime of x. So let's simplify this. I've got two g of x's here, so I'm going to combine those into a single g of x squared. And now look at this. By the commutativity of multiplication, this is a g prime and a g squared. This is a g prime and a g squared. I've got 2 here. I've got 1 here. So those, I can bring them together, and that gives me 3 times g of x squared times g prime of x. And look, by golly, power rule, if I differentiate g of x to the third power, cubing is the outside function. Applying the chain rule, the 3 comes down, replace that with a 2. That's exactly what I have here. And then you complete by multiplying by g prime. That's exactly what I have here. So this shows that the derivative of g of x to the n is n times g of x to the n minus 1 times g prime of x. This is a very important application of the chain rule. And you see here, we can prove it using the product rule. Okay, when n is a counting number. Okay, so I highly recommend that you spend some time between today and Wednesday practicing the chain rule with some simple examples. Check your work by plotting the graphs to see if the graph of the derivative that you get looks like it should be the graph of the original function that you're given. We're going to use the chain rule a lot. It's super important. Okay. But I'm going to leave it there. It's 9:50. I'm ending right on time. Jet, you had a question on homework, so hang around for a second. You can ask it. Anybody else that wants to hear it can hang around too. Otherwise, I'll see you all on Wednesday.
Okay, so okay, it is on exercises 3.3, which is on page 263, I think, in the book. So basically a couple of sections. That's as far as I've gotten so far. So far, it's been great up until I got there and I was like, what? So the sections from like 122 to 125, and then 126 to 129, where they're using that table. And I don't know, maybe I was just like really tired by that time and my brain just didn't want to go there. But so
you're talking about the numbers 126 through 129?
pretty much.
Okay.
So yeah, I think it's, for me, when there aren't just obvious numbers and I'm tired, then it's just like hard for my brain to like, you know.
Yeah, no, I mean, it's really hard to do math when you're tired. It's really hard to do new math when you're tired. So let me tell you that you're probably making this more difficult than it is. And that's because it's a new context. Seeing that table of numbers kind of makes you go, oh, holy crap, what's going on here?
Yes,
but so let's look at problem 127. Number 127 says, find h prime of 2 if h of x is f of x over g of x. Okay?
Right.
So let's set this aside for a second and just notice that we want to calculate a derivative. Okay, so you look over here and you say, hey, we've got the quotient rule, so I can calculate the derivative of that. That's a piece of cake. H prime of x is the derivative of the top, oops, times the bottom, minus the top, times the derivative of the bottom, all of the bottom squared. Oops, not the bottom squared. You good with that, Jet?
Yes.
Okay, piece of cake. Now, you go back and look at this. All right. Oh, hey, you're halfway there. You've got the prime. Now you want to know what the 2 is. Okay. So we'll just go wherever there's an x, we're going to put a 2.
Okay.
Now you say, what the hell are these function values now? How do I find them? Well, when you look up in the table, you say, oh, look, there's a row for f prime and there's a column for x equals 2. So you just use the table to look up these various values. They're all there in the table. Does that make sense?
Okay, so I'm at like g prime of x, and then at 2, then that's 1. Am I reading that right?
Yep. Yep.
Okay.
G prime of 2 is a 1. What's f of 2?
Um, 5.
Yep.
Okay.
Yep. And so, all the numbers you need are going to be in that second column, because that's the column that goes along with the input x equals 2.
Okay. Got it.
Okay.
Yeah, I was making it more complicated. I was just saying like everything everywhere. Like I said, it was probably 11 at night. I was like, forget this.
Yeah. So that's all it is. Your brain was thinking about it overnight. Now you're refreshed. Now you see how this works. This is often called a lookup table. It's a numerical way to describe a function. That's all this is. So it's asking you to bring your formula together with the idea of numerical functions.
Okay.
I find them go ahead.
No, go ahead.
I was going to say, I find this kind of stuff a little bit annoying, but it's the way some things work in the world, and you just have to deal with it. So.
And how much are we needing to? Because my biggest fear are word problems. Because it's like when it comes to something new, a new concept that I'm learning. So I typically have a tendency to get to the word problems and go, nah, I think I'll pass. So when doing this homework assignment, like how much should I like really plow into?
So, I hear you when you say when you're tired, you hit a word problem. It's like your eyes are crossing already, and you can't really think about them. But word problems often have you bring things together, and they often have you connect the real world with the theoretical math world. So there's value in it, and I can understand your defenses are down by the time you get to them, because they're usually at the end.
At the end, yeah. And I'm sure probably when I take my physics class, when I get there, it's probably going to be a lot of word problems, I'm assuming.
It's probably all word problems, right? And so it's good to start exercising skills and habits and strategies for doing word problems here. And so I try to bring word problems into class when I can. But don't hesitate to, if you start a word problem and you get stuck, don't hesitate to send me a text or send me an email or bring it to class and bring it up. I think they're good to start. They're good to work on and chew on. But I totally understand, when you're tired at the end.
We had one in one of the last learning target quizzes that I did.
I will do that once in a while. Yep.
Okay. All right. Well,
Okay.
I do have to work. Otherwise, I would take up way more of your time.
Yeah, I got to get to class here in a minute too. So.
All right. Thanks
for sticking around.
All right. Okay. Bye. Have a great day.
Bye. You too.